How do you prevent all the signatures from collapsing on each other, right? Because that's a very nice way to cheat, right? I mean, and you know what neural networks like to do, right? They like to cheat.
Hi there. Today we'll look at Dynamic Inference with Neural Interpreters by Walid Gondal, Nassim Rahman, and others. So this is again a paper where I will interview the authors of the paper. In fact, we had three of them, the two first authors and Francesco Locatello as well. So that's going to happen in, I want to say, 10 minutes or so. If you already feel comfortable with this paper, you please skip ahead to the interview part. It is by far the best part of this video. I will give a very brief introduction to this paper by myself right now so everyone knows what's going on. We'll go over the architecture again in the interview just because I want to get it from the authors as well. So briefly, this paper takes a new look at how we build neural networks. Specifically, it supposes this architecture called neural interpreters. And these neural interpreters, as the title says, they're able to do something that the authors call dynamic inference. I want to jump right into this. What is a neural interpreter? Now, what we're going to see in this model is a lot of things, a lot of maybe things that are familiar are going to be rephrased in sort of a new terminology. And that is because the thinking that leads to this model is different. The thinking is something like, well, if I process data, I'm going to do so in a series of abstract, let's say, functions, a series of abstract functional modular components. And what I do is I compose these modular components in my head or in the computer when I program it in order to achieve a certain goal. And we're trying to replicate this in a neural model. This is going to look a lot like a transformer model, but it has a few intricacies that make it particularly suitable to this formulation. And this model here, it's not going to be like the next state-of-the-art model on ImageNet or anything like this, but what it is going to be able to do is going to be able to generalize to unseen data, especially in terms of data that needs some sort of a logic processing, abstract reasoning, or anything like this. It's going to be able to do this, and it's going to be able to handle things like distribution shifts or just very little training data much better than a regular model that I just train on a training set. Of course, this model is trained on a training set as well, but you know what I mean. So we're going to focus on models that abstractly work a little bit like transformers in that the input is going to be some sequence of tokens, like a set of tokens. In this case, it's a set of visual tokens, which are going to be converted to visual embeddings, but you can imagine any sort of token-based input, such as text or little snippets of sound or anything like this. Whatever you would do to a transformer currently, that's the same input that this model gets. The model is made up of this series of scripts, what they call scripts, and these scripts are nothing more than just blocks of computation. A regular transformer also has blocks of computation. This model does as well. Nothing special here. However, inside of a script, now the differences start. So inside of a script where a regular transformer will essentially only have what you see on the right here, it will have a stack of attention layers and multi-layer perceptron layers interleaved with each other. This script right here, it modularizes this into what is called functions. So each function by itself, for example, here you see F3 consists of a bunch of these layers. Yet there is also F2, and F2 will consist of different ones of these layers. In fact, they do share some parameters, but we'll get to that in a minute. So F1, F2, and F3, they are all independent functions, independent from each other, and any token can be routed to these functions independently. So the idea is that we take the tokens, and the tokens are routed to either one or more or multiple of these functions, but not all of them. The goal here is sparsity. So each token is routed to a few functions. Each function takes as input all the tokens that are routed to it. it internally runs these layers right here, and then it outputs the tokens again. And what happens then, again, is special in that in a transformer, we would just go on to the next layer with the next set of parameterized functions. However, in this case, we apply the same layer again. You can see here the top and the bottom are the same. So we do the same thing with the output. We again evaluate it, we route it to different functions. So the same token can first pass maybe through functions 1 and 2, and then the output is combined from them. And then in the next step, we apply the same layer again, and maybe then the token is routed somewhere else. Maybe then the token is again routed to function 2, but now also to function 3 instead of function 1. So this is supposed to represent this, first of all, modularity in that we have different functions, but also composability in that we repeatedly apply the same layer. So weights, the computation is shared. This is essentially a recurrent layer right here, and you can imagine that there's not only 2 applications, in fact, I think they go up to 8 applications of the same function within one script block, yet the functions, they're modular, they're independent from each other, and between each recurrent step, a routing table is computed anew. Note that this is not the same routing as happens in the attention layer. The attention layer here is part of this. So this attention layer here would be, for example, right here. It would actually be a part of a function. So the attention layer would only consider tokens that have initially been routed to function 3. So now the question is, how does this routing work? And I also said a little bit that code is shared, or weights are shared between the functions. I want to tackle the second thing first. The way this is implemented, and we come to this all in the interview in more detail, and I think what I understood is not necessary what I'm telling right now, what I'm going to tell, namely that these function 1, function 2, and function 3, they do share some of their parameters, but not all of them. In fact, the authors here imagine a scheme where each function has a global set of parameters, let's call them W, and then, so function gets W, which is a global set of parameters. It gets the input X, right, which is the token that is currently being processed, and it also gets C, which is the code of the function. So this here the authors call the code. And the idea is that this thing right here, that's shared across all the functions. There are parameters that are shared, and then there are parameters that are just individual to each function. The idea is, as I said, the C is the code, and this W right here you can see as the interpreter. So this is in analogy to, you have sort of an interpreter like the Python interpreter that has code by itself, right? Python is written in, well, CPython is written in C, so there is shared code among all Python programs, but then obviously there is also individual code for each Python program. They see these functions in the same way. They have a set of learnable parameters that are across all the functions, which are kind of global interpreter parameters. And then there are local parameters, which they call C, which they call the code, which are also learnable parameters. They're nothing else, but they're just localized to each function. And that's what makes one function different from another. Every function here has learnable parameters with the code, which is individual to each function. As I said, is not necessary. Like, you could just imagine that these be completely independent neural modules. They will have independent attention weights. They will have independent multi-layer perceptron weights. This will still be the same model, but it's just in sort of an homage to this thinking of dynamic computation that the authors here build in this weight sharing scheme. So the second thing each function learns by itself, it's what they call an S variable. I believe it is S. And this is what determines which token is routed where. This is a little bit like in the attention mechanism, every token exposes a key and every token exposes a query, and then keys and queries are routed according to inner product. Here, every token is run through essentially an embedding layer, a linear layer, which determines to which function it's going to be routed. Each function has, as I said, these S variables, which are just vectors. And then we compare inner products. So again, each token goes through this type inference function, which is a stack of neural network layers. We obtain an embedding T. We look at the inner product between T and what they call S. S is a vector for each function, and that determines what's routed where, right? This is an exponential, this is a normalization, so this is a softmax routing based. So if you have function 1 here, function 1, if you have function 2, function 3, and you have your tokens, right? Each token is sent through the same neural network to determine its what they call type. Essentially, it's an embedding, right? This is type 1, type 2, this is the type of token 3, and so on. Each function will already have as a learned or fixed parameter, right? They, in their model, they suggest one can learn these as well, but in fact, they say it works the same as, when you just leave them fixed. So they uniformly initialize these S variables. This is S of function 1, S of function 2, S of function 3. S stands for signature, I believe. So the idea here is that the function exposes signature that tells which variables are even allowed to go in the function, and the tokens express a type, and the type and the signature needs to match in order for a token to be routed there. And the matching is done obviously via inner product. So for example, these two are certainly going to be routed together because their inner product is going to be large. As I said, this is not too different from like attention-based routing, except that this is dynamically computed. However, this here is either learned or fixed. So in attention, this would also be dynamically computed. But since the functions aren't dynamic, this could be a good extension somehow, thinking that the functions themselves could be sort of dynamic. But then I almost believe we'd end up kind of at the classic attention mechanism, because maybe you want to compute the functions from the sequence here itself, right? The code and the routing, which would essentially be the keys and maybe the values. Not super sure. But yeah, so another idea I had just after the interview is that they say something like, these signatures right here, if we want to make them learnable as well, the neural network could sort of cheat and collapse them all together so that every token is routed everywhere, which I think due to the nature of gradient-based learning would be advantageous at training time. But it's not necessarily what you want for generalization. You would like to preserve the sparsity aspect for generalization. And they talked about having repulsion losses between these. Maybe one could also take ideas from VQ, like from vector quantized VAEs or so. They do have the same problem, right? That their codebook needs to be not collapsing. And I think the quantization procedures that they have there, as well as the methods they use to construct the codebook, could be instructive for here, rather than just leaving the things at sort of the uniform initialization. In any case, this determines how the things are routed to the individual functions. It, by the way, also determines how they are combined again, which is something we didn't talk about in the interview. So the routing table determines how the tokens are routed, but then also the combination happens in sort of like the reverse routing table. Obviously, because you only want to get output from where you got input. I believe at least that's what's happening. Yeah, I think so. Otherwise, I might be wrong here. The attention mechanism inside of the function happens as a regular attention mechanism. It is obviously gated by these C values right here, and those are simply the values we've just computed, these routing values. This essentially just means that every function only has access to the tokens that had been routed to that particular function. Then there is an MLP after the attention layer, and the MLP is represented here. Again, these are all these ModLin functions. These are linear layers that, as an additional input, get this code. And the code is essentially the parameters that are special, as we discussed before. So they have a formula here for these ModLin layers, and the ModLin are also used in the attention layers in order to compute keys, queries, and values. So you can see right here, ModLin is computed out of an input and a code vector. It is computed in the following way. It's in a classic fashion, it's W something plus B, so it's a linear layer. However, W and B are shared across all of the functions in the same script. Then the something right here is the different part. So there's the input, but it's element-wise multiplied by, okay, this is layer norm, and then this thing right here is the code projected through this linear layer. The WC linear layer is also shared across functions, but the code is obviously different. You can see what differentiates one function from the other one is simply the code that is input to the function. Everything else is shared across all the functions in the same script. This is, again, not something that is, I believe, necessary to the splitting up of the functions. You can imagine every function having its own independent set of parameters, but it does sort of goes one step more into this direction that the authors want to go right here. So then you can build up things. So you can build up MLPs as a combination of these modlinear layers. You can build up mod attention layers, which is simply attention, but instead of linear layers to compute keys, queries, and values, you use these ModLin layers that get the code. So even in the attention, most of the parameters are shared between the functions in the same script. Then you can build all kinds of things from these. So a line of code is essentially one of these blocks that has an attention followed by an MLP, which we saw like on the right side. So this thing here, that's a line of code. Then you get from lines of code, you can determine what is the interpreter, which is many lines of code after one another. Then you can iterate these functions. As we said, we apply the same function multiple times. So the interpreter now is applied multiple times, right? But always, we always do the type inference, the routing in between. And then obviously you can apply that many times over, and that will be the whole model. So these are the different scripts that you apply. So here inside a script, function iterations enable sharing of computational units in depth. Increasing the number of function iterations can increase depth without increasing the number of parameters. So it's a little bit of a recurrent scheme inside of the big blocks that make up the entire model. All right, that's the entire model right here. I hope you could sort of follow. We go through it again in the interview, so I want to keep this really brief right here. I want to go down a little bit to the experiments. Right now, they do experiments on learning fuzzy Boolean expressions. So they have these Boolean formulas and, not, and or. These are fuzzy, so they deal with real numbers. And on the other hand, they also look at actual real data. So there's image classification as well as these abstract reasoning matrices over here. They make some interesting discoveries. For example, they can learn the Boolean formulas by only adjusting the routing parameters. Oh, I've scrolled too far. So by only adjusting the routing parameters, they can learn these Boolean formulas and generalize to new ones. I said this wrong. They learn the Boolean expression task by training the model regularly. Then they can generalize, they can transfer learn to new ones by only adjusting the routing parameters, which kind of tells them that the function modules they learned, they are in some way kind of universal. They represent these Boolean functions on a more fundamental level, because you only have to adjust the routing in order to make them adapt to new things. The second thing, they look at sort of how samples propagate through the network. I'm gonna ask them in the interview about this graphic right here. They look at the inferred type embeddings and see that really they do not all collapse to the same thing, right? As you can see right here. They also look at how this develops in function iteration. So they say types are more clustered in the later function iterations, suggesting that the input set elements gradually develop a type as they progress through the network. They do a lot of these kind of little experiments right here on toy data, on real data. They even look whether they can drop out functions or add in functions after they've trained. Yeah, so that's what they did. But I will ask them all of this in the interview. So I don't want to go too much here. In essence, I have to say I did like this paper. It is quite hard to develop a model like this and then design experiments that really validate that what you think is happening is happening. And I think the authors did a good job. I'm still not 100% convinced, but I think that's never going to be possible. I think the authors would agree with that statement. It is hard to peek into these models. They do test on real data right here on against some baselines. You can see the results are kind of all over the place. Their models is ahead a lot of the times, not all the time though. So I think the problems are still open and these models are still out there to be developed. If you have ideas, more than happy that you play around with it. I didn't ask them if the code was available actually. I'm going to do that, and if it's available, I'll link it in the description. If it's not available, then I'm sorry, you'll just have to guess around. Yeah, that was it. Now over to the interview. Welcome everyone here back. Very, very fortunate today to not be joined by one author, but actually three. I have with me today Walid Gondal, Nassim Rahman, and Francesco Locatello that all work together on the dynamic inference with neural interpreters paper. Welcome everyone. Thank you so much for being right here.
Thank you for having us, Yannick.
Thank you for
great.
Yeah,
Thanks
for having us.
Yeah, it's really cool, the paper, because I think it takes maybe a little bit of a first principles approach to the whole idea of computation. It is really framed in terms of computation. It is framed in terms of I want to have different modules that do different things. Then it's somehow being connected with neural networks and so on. Can I ask you, what was your motivating thought behind all of this? Like, how did you get to it? Did you sit down and say, well, I want to build a computer-like neural network, or what were the kind of leading thoughts that you would tackle such a problem in this way?
Okay, so I guess I'll start maybe. So of course, I've been in Bernard's group for I think 2 years or more, and also Joshua. And the thing that they've both been very excited about is has to do with principles of causal mechanisms. That's you can decompose the world as a system of modules that kind of interact with each other, right? So that was kind of like always at the back of our heads, right? And then we thought, okay, look, this is actually, the intuitions there is actually not very different from what we do as programmers all day, right? I mean, it's kind of, we type functions, we use functions, and then we kind of recompose stuff, and it's maybe it's not as different as we think. Like, these two things are maybe not very different. And then, of course, since we're deep learners, how do we mash these three things in and make something cool out of it? So I think that was kind of the initial motivation that kind of drove us to it. I don't know. I mean, I guess we had like this chat, I think, and then we were like, okay, this does not sound too shabby. Yeah.
Yeah. And I have to say, like, I read the title, I read the abstract, and I thought to myself, like, this is such a Benjo paper. This is like Joshua Benjo has all over it. And then only then I looked at the author list, and I was like, of course, it is astounding. So maybe, I want to get by the time people watch this, I will have done a little intro, but I maybe want to go with you again, just briefly over sort of the main structure of all of this. So this your method essentially takes the form of, let's say, what we would know nowadays as a transformer network, just broadly, right? So you have a bunch of like input tokens, like down here. In this case, you do you can do multitask classification. That's why you have like multiple CLS tokens. But you could imagine anything, let's say, a transformer network could do, as long as it sort of takes a set of inputs and it outputs like a set of outputs, and every layer, as in a transformer, will take a set of embeddings, presumably, and output again a set of embeddings. So far, so good. But then here is the first thing that's kind of different. So your model, whereas a transformer is made up of multiple, I guess they call them transformer blocks, your model is made up of multiple of these scripts. What is kind of the high-level idea? What is a script?
So a script is, I mean, you can think of it as essentially like a group of layers. Mm-hmm. Like the core of the architecture truly are like the functions and the objects, because I really like this analogy with programming languages, where you have objects that are processed by functions, and then when you have a bunch of functions, you stack them together into a script, and then you can compose a hierarchy of scripts. So this split in scripts is just a convenient way to share parameters in different ways across the architecture, because maybe the early layers want to do things that are slightly different than the later layers, and since all the functions within a script share certain parameters, then you can have a differentiation this way.
Okay, so this is simply because the script 3 is independent from script 2. Script 2 is independent from script 1, and so on, yet within the script, certain stuff is shared. Okay, so it is, okay. Then within a script, right, you have these, what you call functions. And we see right here, there are 3 functions in this example. They appear multiple times. They're sort of functions next to each other. There are also functions one after another. Can you maybe comment a little bit what are functions and how do you sort of stack and combine them?
Right. So we could think of functions as like really the fundamental, like in this case, like a building block of like, it's an abstraction, of course, right? But it's kind of like a building block. It's kind of a unit of computation that can be shared. And how is it shared? It's shared along depth, right? So you see, like you can have a token that goes to F3, and then it may come back to F3 again, or it may go to F2, depending on how it's routed, right? So like there's this reuse of parameters, like a dynamic reuse of parameters, and you actually learn how to reuse the parameters. And the whole function abstraction is what enables that, right? So along with, it's kind of like horizontally, it's kind of essentially a way of adding more capacity, if you can think of it that way, right? And horizontally, and vertically, it's kind of like adding, it's adding depth, of course, but like it's adding more
computation.
More computation, exactly. And it's and we have some actually pretty fun results downstairs where we actually show that this amount of computation is kind of flexible, even at test time. And so
you split this up right here on the right side. So this would be sort of what a function looks like internally. In fact, you have a stack here. This stack in depth. Do I see this correctly? That's sort of the front. Let's say that the front thing of the stack corresponds to the pink function, and the second one would correspond to the blue function, and the last one corresponds to the green function. So each function essentially is a stack of neural network layers, abstractly spoken.
Yes, but then they also share parameters, right? Because this distinction is modulated with the code of the function. Again, if you follow this programming language interpretation, like you have the code that determines what the function does, and then to make it easy, then all the functions actually share parameters, but then they are differentiated by the code and their signature, of course, that determines what they are able to digest.
Exactly. Yeah, that's exactly that. Those are two things that. So you just said, which is one of the questions I actually had about, where exactly are parameters shared? Because if anything, this method seems like a sort of an intricate way of sharing parameters between things, right? You just said there are parameters shared between all of the functions.
Yes.
Is that correct? Okay.
Yeah.
Now, what differentiates the functions from each other is what you call their code and their signature. So if I have any sort of token, let's take one of these tokens right here. So what do? This is like xi, my token I, and I have a bunch of functions right here. Every function is characterized by its signature and its code. And its signature is, you call it S or some S, I believe.
That's right.
So S, J, and S determines whether or not the token is even routed to the function, kind of, right?
So S is about what the function is able to process. And then you'd have to look at what's the type of your object. And then if the type matches what the function can process, then it can be processed.
So you run a function through this type inference function, which I'm going to guess is like a linear layer or something like this.
2 MLP layers.
Like or multiple layers. You get out an embedding, and you calculate the inner product between this thing and whatever this signature is per function. Now, I understand correctly that your framework suggests this could be learned, these types of functions. So every function would sort of expose a type, very similar to how in an attention layer, every token exposes like a key to be addressed, right? And then whatever the type inference module expresses could be interpreted as sort of the query, and you would route queries and keys that have large inner products together. However, if I understand correctly, in your experiments, you just left the type signatures at the initialization. So you were happy saying we initialize them uniformly and that's it.
That's one way of doing it. I mean, even if you don't do it, it kind of still works. But I mean, this is just like we found it to be, I mean, we also experimented with some sort of a repulsion loss where we could kind of, so to give some more context, that was kind of, like how do you prevent all the signatures from collapsing on each other, right? Because that's a very nice way to cheat, right? I mean, and you know what neural networks like to do, right? They like to cheat. So like this, like not learning SI is just like it's just the simplest way to, like prevent this from happening. We experimented with some other ways, like, I don't know, a repulsion term, like a hinge repulsion term, right? That would kind of just push everything away if they're like too close to each other. It worked just as well, but, had more hyperparameters and thought, okay, how can we simplify this? How can we break it down? And then we kind of, just froze it and saw, oh, okay, the performance is not too bad. And the reason we understood was that, okay, the type inference can also do, because SI is a learnable parameters, but the type inference MLP is a 2-layer MLP. It also has learnable parameters, right?
Yes.
And their roles are kind of sort of interchangeable to some extent. So we kind of, okay, that's like, we figured out that's like one way to save some complexity, essentially. So
you have two things that essentially are learnable whose mission is the same.
Exactly.
Yeah.
Exactly.
Okay, I see. Yeah, and then you do this. This is I think the whole thing is a softmax. Then it results in sort of a softmax. There is an exponential of the inner product, and then there is a normalization involved, right? So this is essentially, let's say, an attention mechanism over functions.
If I understand
over the
this
input, right? Because this then produces a mask.
Exactly.
Yeah. So this determines, you have this nice graphic right here, this determines which token is routed to which function. And the same token can be routed to multiple functions, but hopefully you've configured your threshold such that it's reasonably sparse. So did you, I don't know, was it your Was it your plan to have this as sparse as possible, or what is the reasoning behind here? I know sort of the people who argue from neuroscience and so on, they always argue for sparsity. Only a few of these modules are activated at any point. Is it hard to impose this in a system like this, or how does that work out? I imagine it's going to be easy to like have one function per token. I also imagine it's going to be easy to have all of them, but to have like a sparse in-between thing, is this a hyperparameter that is very hard to figure out, or is this relatively easy?
So I think like we found like a good range of hyperparameters which kind of did the work in, and actually like we have like a whole big appendix on like how we like how to set hyperparameters based on the problem that you're looking for, and like the behavior that you're looking for, right? Because in the end, what you have is a spectrum, right? I mean, if you have too much sparsity, your thing is going to be really hell to train, right? I mean, you're doing gradient-based learning, right? I mean, there's like only so far you can go unless you try some combinatorial magic and get it working. So it's like not a silver bullet in this sense, right? But there's a trade-off between training stability and kind of like sparsity and out of distribution performance. We found that under some configurations, training went like super smoothly, right? And then when we tested it on some adaptation tasks, it was meh. But then we had like, when we cranked up the sparsity, like most of the runs diverged when we cranked it to the extreme, right? But when you crank it a bit less, like on the edge of chaos, that's where the magic happens. And that's where you get these models that perform well in distribution and are also like pretty good for adaptation task or the other tasks that we're also interested in due to the inductive bias. So it's kind of always like playing the daredevil, like how far will you go? So given that this seems to be a distinct point, is there a hope that we can automatically discover this point maybe in the future without having to set a hyperparameter to be like, at this edge of chaos where the magic happens? Yeah, so like I mean, that's what hyperparameter search is kind of about, no? I mean, that's what you're kind of. I mean, the edge of chaos is definitely not a new thing. I mean, I think pretty sure there are a few papers on it as well. Like, it's a pretty common thing also in neural networks in general. So, so it's definitely not a new thing, and maybe there's a more principled way that we're not seeing yet. It'd be cool. But I think so for this paper, what we just did is just like tuned some hyperparameters, and it was not awful, right? I mean, if you did not, so if you kind of, even if you did not go too sparse, it kind of worked, right? And then the performance, I mean, the less sparse you go, the more more stable the training is. But like there's like some leeway, and it's like not an awfully tight tolerance. Sorry, Francesco.
Yeah, and like I think like if you want to be extreme about this, you could also think about like playing with it during training, right? Like instead of like fixing a value, you can train the network to exhibit different behaviors depending on like different type of sparsity you may want to use at test time, and then you just decide later on, okay, do I want to be conservative in my prediction or not? Whether I believe this data is in distribution or not, and then you use different degrees of sparsity. This could also be done. We haven't tried. Maybe it helps stabilizing training because you also allow for like less sparsity. Also, at the end of the day, there is an exponential in front, right? So like small values get killed anyway.
Okay. Yeah, that's what I meant. Like probably one, like having one dominant value is also pretty easy. Multiple may get a bit okay, but now this is the part that routes, let's say, the tokens to these functions. You call it type inference, but in essence, it's like I think it's fair to just call it sort of it's a little bit like attention-based routing. It's a softmax over inner products with the things that are available, and the inner products determine sort of the routing table.
Not entirely, right? I mean, it's not like exactly an attention mechanism, but this is kind of like another layer of attention, right? It's kind of like, if you want to think of it like a nested attention, right? Where it's the second attention, like the higher level attention decides which token get to interact via that function in the lower level, right? So it's kind of like a hierarchical attention of a sort, if you want to think of it that way, right?
I mean, it's an attention in front of the attention, because now we actually get to the attention, which happens inside of these functions. You've already alluded to the fact that there are inside of these functions, there is something happening. So I also had a bit of trouble understanding this just from parsing your math a bit, but I think what you said right before helped. Namely, you have these, you have what you call ModLin layers. What does mod stand for, by the way? Modulated. Modulated linear layers, of course. Now, the modulated linear layer is a linear layer, right? Which means it's a W, or it's W times something plus B. So there's a weight matrix, there is a bias, but the something in between is a little bit different. You don't only have the input, but you have the input, and this is the element-wise product with this thing right here. And okay, we have a normalization layer, but essentially, again, it's a linear projection of this C value. And so this is WC times C. And the C comes from here, so that's actually an input to the function. Now, is it like, do I understand this correctly? This is a learned set of parameters that is shared among all the functions in the same script. Is this...
That is correct.
This is what I understood before.
That is absolutely correct. That's totally correct.
Good. Yeah. So, but yet this C right here, that obviously says how one function is different from another function. Otherwise, and this W is also shared between all the functions?
Which one?
Okay. All the parameters are shared except whatever X is element-wise multiplied with. That is the thing that's not shared. So this is, I think your analogy is that C here is the code of the function. That's how you tell the function what to do, and then X is the input, and the rest is essentially the same across all the functions. So you kind of parameterize the function with its code. It's a bit like a Turing machine or so.
I mean, it's not a new, like, it's not a totally new thing, right? I mean, I think we cite a bunch of papers as well, but like, there are like a class, I mean, StyleGAN uses something kind of similar, if you think about it, right? And as does SIPs, like conditionally independent pixel synthesis, and like, they serve as pretty strong inspiration for this setup, right? So I mean, I don't think in this part we reinvented the wheel.
Yeah, sure. No.
It's just like there might be other parts.
My question is, where does the code come from? Because I clearly see that, here is, a token. The token gets routed to one or more functions. So the X comes, that is the token, that is the input. Now, where does the code for a particular function come from? Is that also just like a learned parameter for each function? So F1 has its C, F2 has its C, F3 has its C. Okay. I mean, another way to write this, if I were to sort of draw this up, is that instead of drawing this, right, I can also say, well, there is a this here is also just kind of a weight sharing thing, right? It's a learned parameter times another learned parameter, except one learned parameter is shared across all the functions and one learned parameter is separate per function. So this, if we leave away the weight sharing part of that, it's a set of learned parameters for each function. So I can imagine my X, and here is my C that is one per function, the x and the c, it gets multiplied element-wise, and maybe here is c2 and c3, so that gets multiplied element-wise as well, and as well. So the x goes into each of these, and then all of them, individually, all of them go through this same linear layer, this outer linear layer, which seem to be completely shared, right? This w, so this is like w x, whatever comes out of this calculation plus b. Okay. So essentially,
Sorry, a good abstraction to think about this would be like really an interpreter in Python, right? So that is kind of like an adage to the whole name, right? Because like you may have different functions, right? And these functions, they have their code, they may do different things, but in the end, the actual interpreter that's doing the computation, it's shared between all the functions.
Okay.
Right? So like
so this would be the interpreter here.
Yeah, like the
because
orange
that's
parameter.
Shared.
Yeah, the part that is shared between the functions, those are the interpreters. That's, I mean, you can think of it as parameters of an interpreter.
So this is a way to, I would like, it's again what I said at the beginning. It's sort of just an intricate weight sharing scheme to characterize a linear layer. It would work independently, right? The type inference module would work independently from sort of the mod linear layer. These two we could make separate models with either one or the other.
Yeah, so you can, I mean, so like the X's, right? I think that's where the signatures and the type inference thing comes in, right? So if if a function C1 like sees X, or if it just sees zeros, like in a naive implementation, right? That is what's determined by the type inference mechanism. Right? But otherwise, I totally.
And that's what breaks the symmetry a little bit, right? Because now we are sharing parameters in both width and depth. So I mean, it's clearly you want to differentiate a little bit what happens, right? And that's how it happens essentially.
Cool. And you use this mod linear layer, which so its input and output are as a linear layer, or you input a token and that will output another embedding for that token. And you use that in sort of the rather classical way of doing attention. So you compute keys, you compute queries, and you compute values from the token using these mod linear layers instead of just linear layers as we would do it in regular attention. And then the attention mechanism is essentially the same, except, of course, it needs to respect that routing table, right, that we computed initially. So any function, so the functions here are essentially attention mechanisms, yet they only get access to the tokens that the routing mechanism determined would be appropriate for those ones.
Yeah, you can really think of it as a sparse attention that doesn't get all the tokens. It's gonna get a subset of them.
Yeah. Okay, so now we have the sort of attention matrix, and we can again use a linear combination here and send that as a classic attention mechanism does through another linear layer in order to get the output embedding of a particular token. Is it usually in, let's say, regular attention mechanisms, this part here takes quite a lot of parameters, which is, it doesn't seem like it. Like it doesn't sound like, it doesn't look like much, right? But it does take like a lot of parameters and computation. Does the fact that you parameterize things with these codes, does that change how many parameters there are in different parts of the model? Can you save a lot of parameters using these weight sharing schemes, or like what do you, is it a side effect of your architecture that you also have less parameters, let's say, in
I mean, because they're shared everywhere, right? So at the end of the day, you have less parameters. It doesn't mean that your inference speed is going to be faster, right? But definitely, it's a very lean architecture in terms of number of parameters.
Yeah, that's what it seemed to me. Yeah.
You're sharing it in
Exactly.
depth, right? So that's where, yeah. But you're also kind of not totally sharing it because it's codes that kind of also run the show. You're kind of sharing and not sharing at the same time in a very special way. So I think that's that's the shtick, I think.
So coming back, exactly. Coming back to this diagram right here. So F1, F2, and F3, they all share the same sort of global parameters, but then F1 has its own code, and F2 has its own code, and F3 has its own code. And what you do now, that's what you said just now, is we apply this layer recurrently. Right? We apply it multiple times within each script. So potentially that allows one particular token to first go through function 1, have a result computed from that, then go to whatever function 3, have a result computed from that, and so on. So the code for function 1 would always be the same, independent of which step it is applied. So this really feels like I'm a programmer and I'm composing functions one after another.
Exactly, and then it's nice because you can do it in a totally flexible way, right? After function 3, you could go back to function 1 again, and or use function 3 again. Like it's completely like the way each example is routed through the network is completely independent.
Yeah.
And is determined on a per sample basis, right? And the routing itself is completely learned. So that's why it's a very interesting architecture.
Yeah, I see that. Yeah, that's pretty cool. It is implemented, I see, like as a recurrent neural network, right? I mean, essentially I apply the same function over and over again. Parameters are shared across the depth, which is kind of akin to a recurrent neural network. Did you have to do any sort of tricks in order to get this to run stably or anything like this? Did you notice anything? Like how much stacking did you do in depth? How often did you apply each line of the script?
Oh, that's a very, 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 it's an excellent question. So like, so I think we talk about it at great length in the appendix, but nevertheless, what we tried was kind of, so we went, I think the biggest models we trained were like 2 scripts, each with 8 such recurrent layers, if you want to think of it that way, right? So such function iterations, that's I think how we call them. And that worked essentially without much of a problem, right? And we tried even some combinations, for instance, like 2-2-2, which means like we had 2 scripts, and then 2 iterations per script, and then there's another aspect over here, which is kind of how many, like inside, the MLP attention,
That's
you
here.
can you can kind of keep adding more to it, right? So that's kind of like another hyperparameter, and we found like 2-2-2 also works pretty well, like absurdly well, which was interesting, and like 8-1-1 also works pretty well, like 8 function iterations, 1 script, 1.
But that's also why you want the scripts, right? Because it breaks this chain. And allows you to not have a chain that is too long. And, exactly. You can think of it as a way to break the recurrence.
And between the ones inside here, like this, let's say this MLP and this MLP, are these the same functions? Are the parameters shared, or are these 2 different functions that now that live inside of these functions?
They're different.
They're different. So you have different functions here that get repeated here, and then you have different stacks of these repeated applications of different functions.
Okay, that's right.
So the real recurrence here happens in step number 2. That's where you recurrently apply the things, and inside of the function, it might take more than 1 layer to make the function, powerful enough to do its computation.
Okay. Exactly, that's the right intuition.
Okay.
Yeah, and
so I see. Yeah, sorry. Go ahead.
So there is some lag, but I just wanted to say, I mean, we also tried to increase this recurrence to depth 16, and I remember it worked as well. Like, I mean, there was no issues. and we shifted from two
Yeah.
different tasks, like from this multi-task classification to this reasoning task, and the parameters we kept them the same, and they were out of the box.
Yeah, it's a little bit like, so I see a little bit, you combine a lot of things obviously here, because I can also think of a regular attention based transformer where I have, let's say I have this here as a block, and I just repeatedly apply the same block. I think didn't like the Hopfield network paper or so even make an argument that that's sort of connects transformers to Hopfield network, but that was always sort of the entire attention. So I can imagine that by itself. I can also imagine what I said before, this routing just by itself. In fact, I believe the sort of mixture of experts idea is very much akin to that, where you say the MLP here, as I said, it takes up a lot of computation, and I can route the tokens sparsely to the individual experts, yet you decide to sort of split up the entire layer altogether. And that, yeah, I think it comes from different motivations, because the mixture of experts obviously comes from the motivation that I don't want to, I want to shard my model somehow. But that means that doesn't work super well with the sparsity that you do in the attention mechanism. But I don't want to.
But if you think about it, like this could also be a limitation of our approach, right? Because now every example has its own independent path through the network, and now you cannot really exploit like batch statistics, right? Like now I could say, okay, I have this batch of examples, and they look like they would all benefit from this particular path in the network, but you're still deciding on each of them independently, and this has the drawback that you need to keep every expert around.
Yeah. So if I were to describe your model without, let's say, the language of this functional approach and so on, because you introduce a lot of new words like scripts and functions and lines of code. Like there's lines of code, which so there is the interpreter, right? And the interpreter goes across scripts, and every script is, wait, I had it before, is like composed of different lines of code. And each lines of code shares the same functions and so on. If I describe this, let's say, without any of the language, I would say this is a transformer-like model where each data is divided into blocks. Each block is a recurrent application of a fixed layer of attention mechanisms. The attention mechanisms are separated into individual modules that in parallel can process data, and then you route that data sparsely to these individual modules you do this recurrently, so the modules can dynamically process these inputs. Okay, what you did sounds a lot cooler than this, and I can totally see that you come from this very different point of view, and I think it gives rise to a very interesting model. So now it came to the point where you did some experiments to validate this, and what is especially interesting, of course, are your hypotheses. What kind of hypotheses can you even make building such a model? Like, can you lead us a little bit about how you approached the experiments? Because what's boring is, we get better on ImageNet. Also, probably that's not going to happen, right? But you need to, and I think this is maybe a little bit for researchers who are starting out, when you have this new architecture where you think, aha, okay, this does something new, how do you design an experiment that sort of validates, yes, that's really what's happening? Like, how do you approach this?
Yeah, so for me, we have 3 experiments, right? But for me, there are really two clusters of experiments, right? The one on more like real data is about can I solve both classification and reasoning with the same architecture? For me, that was the most interesting part. And then, of course, like I want to see all the advantages of the modular computations. I want to be able to change the inference time, adding modules, dropping modules, and whatnot. But for me, the crux was really like, can I do these two tasks that are seemingly very different? And then the other part on the toy experiment, it was really about can we truly validate that these functions can be composed in novel ways? Because when you go about it on the visual data, for example, like, I mean, it's really hard to say exactly what is happening, right? But then my favorite experiment is when you train the neural interpreter on two like logic rules, and then you can extrapolate to unseen logic rules that then can be obtained as a composition, right? And you can do that only changing the routing. Then it means that the network actually did learn some compositional knowledge, which was our goal to begin with.
Yeah. And so that's what you did. You did here. You took these logic formulas and you built a data set from them. You know, you have and not and or, and these are all fuzzy. So these are not Boolean logic, but they're you know made out of real numbers. And is a multiplication. Not is 1 minus, and so on. And you can now build Boolean functions. You can sample them, of course, in some interval. You can train your network on that. And now you wonder, can it generalize to unseen logic formulas, which would sort of be, if this works, one would think that the network has learned these fundamental primitives of logic.
If I train like learning and, or, and not, then I should be able to recompose my primitives to perform SOR. And I should be able to do that without changing the core, the parameters that decides the computation, but only how you stitch together the functions. That in our case is the routing.
Yeah. So you only changed the routing parameters. Right. Nothing else.
Yeah. Of course, if you change everything else, it works better. But it still works surprisingly well if you only change the routing parameters. And that was the interesting part.
There was this recent paper about similar things that essentially said I only have to adjust the layer norm parameters in order, or there are also these adapter layers, right? Did you compare to anything like this, or do you see parallels between what you're doing and essentially, you know, people saying, well, if I just change, people saying more generally, I can adapt a transformer if I just change like very few parameters in between the layers. Do you see parallels? Or
I think the motivation is different. Like, so there are papers that adapt, for example, like the batch norm parameters when you are on a new distribution, right? And then you can get much better robustness. But for us here is really about getting some evidence that the architecture is able to reuse and recompose these primitives in novel ways. Yeah. So, I mean, of course, like methodologically, it's the same, right? There are like very few parameters that you want to adapt, but the reason why we do this is completely different.
Sure. Cool. But I think at the same time, it's also kind of, I mean, they also from a very different angle, they make kind of a similar point. You know, like I think the paper you're referring to is that transformers are universal computational engines or something.
Exactly. Yeah.
Yeah. I mean, I love that paper. I think it's one of my favorite for since the past few years. I really loved it, and I think, you know, like the message they're trying to send is kind of, look, if you have a pre-trained BERT, it's in some sense it's universal, right? Because the inductive biases of even attention is a good place to start, right? And this is kind of like taking that a step further in my mind, at least, right? And, you know, like building on that.
You go ahead and you say not only should we train like layers of these attention computations, but if we structure them in certain modular way, that might lead to even more, let's say, universality of computation.
Yeah, that's it. And another North Star, I think, has also been kind of like our 2019 work, the Benjio et al. Work on meta transfer objective for learning disentangled causal mechanisms. And I think the argument there is like, if you have a good modularization of knowledge, then like when given a new data distribution, you should get away really easy when it comes to adaptation, right? Because you're already kind of have all the pieces together, and when you see a new distribution, you just need to change, like do small localized changes, and then you're good to go. Right? That's kind of also been a North Star, as you see, like for the adaptation experiments that come below, right? That like if that also connects with the whole causal picture in some way, right? Not the classical causality, but the causally inspired class of models. So I think that's just like another North Star that has been guiding the hypothesis, because you asked, like how we came up with these hypotheses. And I think that's one of the angles as well.
And like generally, like if you want to connect it back with causality, that has been like a core guide for my research agenda, taking ideas from the causality literature and using them to then develop the new architectures and new neural networks. But then really, there's no causality test, right? So you can only pursue some of the side benefits that you would expect from a causal model. And this ability of recomposing and reusing knowledge without having to use a lot of examples, right? That's clearly one of them. And it's inspired by the paper of Joshua.
And so here you track a little bit how tokens go through this computation graph. And I had I love this line here. There are variations, but also similarities between samples in how their constituent set elements are routed through the network, which I was like, well, what am I supposed to make of this? Do you want to maybe tell a little bit what we can see in this analysis? So these are three different... I'll let you explain it. It's probably best.
Yeah, it's a controversial plot. I think I should take the fall.
And if you're told us to actually push it down to appendix. No, just...
Yeah, Joshua was like, why do we need this in the main paper? Like, does it? But
I'm just saying, what I see is that there appears to be, you say the colored dots identify functions, right? Same color implies shared parameters. So here I see that the same function appears twice always. Exactly. So these seem to be one of these scripts, and this seems to be another one of these scripts.
Exactly.
Right? So then the colors tells me the functions are repeated. Okay, I can accept that. That's exactly as you said. And then I'm somehow supposed to read something from the connection lines.
So what you're supposed to read is that they're not all the same. If you put three samples, if you have three samples, they're routed differently through the network, right? So I mean, it's kind of putting our money where our mouth is when we say that. Like samples are routed differently through the network. Like this is kind of like a visualization of that, right? If you have three different samples, they're routed differently through the network. Here it is.
And I think here it's important, like you don't want to like overinterpret what these functions do on the visual domain, right? Because you don't that's the power of deep learning, right? Like that you have this cascade of computation, and maybe the result in between is not particularly interpretable. And you don't want to read too much into it. And we also don't want to do that, not to over-constrain the network. But then it's important to really show, like if I give you concretely three images, is the computation identical? Because if it is, then we're doing something wrong, right?
Yes, exactly. Yeah, that's what I like. This is because I think in these works, it's always really important to sort of try to check yourself, right? If you're really doing what you claim you're doing. And I see, for example, here the first sample has a lot of connections like in this area, and the last sample not at all. And so, okay, that's kind of what I thought I was supposed to see, but I just wanted to check in with you. And this is really, let's say this is to address the haters that say all your architecture, it essentially, it just does the same thing. It's just kind of, okay, I see. Cool. And another thing that I want to get to is your sort of claims that now I have sort of this dynamic, I can add functions, I can remove functions, and so on. Could you explain a little bit, how do you imagine that? How does that work? What do you mean by add functions, remove functions? Is this during training? Can I do something at inference time? Can I ramp up computation at inference time? What did you had in mind, and what did you do experimentally?
So I think this is my favorite part of this model. So the way you can think of functions is kind of like, I don't know, I like to call it smart batteries, right? So you can install new smarts into your model let's say you pre-train one angle is that you pre-train your model on some data set, right? And then at test time or at adaptation time, you realize, okay, I want to kind of apply, there's a new data set that I want to apply my model to, right? And so you can add a new function that or a bunch of new functions that would kind of nest itself in with the other existing functions and kind of synergize and work together in order to solve the new problem, right? So you can kind of increase the capacity really easily because the interpreter does not care how many functions there are, right? So the way it's parameterized, it does not really care. And so you can add new functions, but what we also found, and I think this was one of the cool rebuttal phase ideas, was to you can also remove functions at test time without any additional training. So you train with 5 functions, and then at test time you just randomly drop 3 of them, and the performance, or 2 of them, and the performance does not immediately tank. It does not catastrophically fail, which is kind of tells you that the
right here.
Yeah, exactly. So it tells you that that the system is kind of
one dropped function is still fine.
Yeah.
Two is pushing it, right?
2 is pushing it, yes.
but it's still not, still not rock bottom. But okay, I mean 3 and 4. I mean, there's nothing left after 3 and 4, right? But
that's nice, right? Because going back to validating your hypothesis, right? This is something that normally is not possible with distributed representation and the typical neural networks we use, right? And then it becomes important to check this, even if it you can only remove 1 function. If you remove 2, the performance is not great. But just the fact that you can do it is something you really need to check when you propose an architecture like this. Because it's part of your hypothesis, right? And you need to design an experiment to test it.
Exactly. Now, when you add and remove functions, do you retrain after you did this, or do you just rip them out and evaluate?
So when we remove functions, we just rip them out and evaluate. Nothing extra. At inference time, no parameters are updated except the functions that are kind of needed. So there's nothing no extra training at all. The model is also not trained with function dropout, which is something one could arguably do, but we don't do that. I mean, the model is trained with all functions, and then it's still kind of, I think it tells us that the functions are kind of a little bit autonomous, and they can kind of they're not, somehow magically they happen to be so, which is kind of cool. I mean,
and when you add functions, let's say you have a bunch of pre-trained model, then you need to sort of fine-tune a little bit in order to incorporate that. Do you have extension ideas to this, maybe to make it fully modular, that I can grab together my functions of different models, or is this anything you have on your radar?
Yeah, that would be kind of I think that'd be nice. Where you have a library where you can kind of pick out the books and compose your own thing. That would be nice. I mean, I don't fully know how to do it. I don't know. Maybe you guys have ideas. That'd be cool.
I mean, it also goes.
It's probably going to the direction of architecture search. Sorry, go ahead.
Yeah, sorry. I was just mentioning that it can also go in the direction of continual learning. So basically, you keep on adding new parameters as new concept comes in, and keep adopting the previous model without losing or catastrophically forgetting the previous knowledge. So it can go in this direction as well.
So we have some very preliminary. Yeah, exactly. Sorry.
You could freeze like the codes to some of the functions, right, as you keep on adding new tasks, and potential. Okay.
And even like just having more like diversity in terms of data sets, right?
Yeah.
You first, I don't know, train on these digits, and then you start doing, I don't know, animals, and then you just keep adding to your collection of functions.
Mm-hmm. And you have the model. You said before you did it on some real data. Can we do classification and reasoning? And could you just briefly tell us how do you assess that the model can do abstract reasoning? It has to do with these matrices right here, right?
Yeah, this is like a fun task, which is for me personally is surprisingly difficult. Honestly, you need to look at these pictures very, very hard and detect patterns, and then you have a list of possible answers, and you need to decide which one completes the sequence. And apparently I'm not very smart, so I cannot do this very well, but somehow, yeah, neural networks can do it, and it's a really fun task because it requires a network to really reason about abstract entities and relate them across the different panels. So there are some logical rules that determines whether a panel is the correct answer or not. And if you have access to the logical rules, it's extremely easy. It's like some quantities are constant, or it's the end of these shapes. But if you don't have the right abstraction, it becomes a very difficult task. And it's really nice that neural networks can do it. And especially they can then extrapolate to new relations that have not been seen in the training set. And that's of course, the performance is bad, at least compared to like the in-distribution performance. But the fact that it's not completely random is pretty nice.
Yeah. And do you have any way or idea, I haven't seen it in this paper, but any idea of how you could train a network on this and then sort of inspect these functions and really see that these logical rules are somehow, learned by these individual functions in some way? Because essentially that's what you would hope happens, right? That somehow these functions, these individual modules learn to represent these individual independent, I'm going to guess the data set makes it clear that these are independent logical rules. Is there any way you could think of to inspect this? Or is like how would you go about this?
I mean, you can try to look at circuits, like the Anthropic AI style, which I find absolutely fascinating. But but it also shows how much energy that takes, right? So you have like really a team working. Like as soon as you have these distributed systems, it's kind of like, and I'm not even sure it will even makes like I'm not sure to what extent these would make sense at all to us humans. Like. I'm not sure what we'll find there. Absolutely, right? I mean, even if at all we'll find the same primitives or not. I mean, I don't know. And I think that's kind of what makes neural networks so exciting. Like they might be solving it in a way that is like totally orthogonal to how we think about things, right? And but we kind of made it at the same time. So we're making something and we don't know what it's doing, which is fascinating. I think that's kind of like that makes the whole deep learning journey worth it, I think. So, sorry, I went on a tangent, but long story short, I don't see an easy way, except the whole like circuits line of analysis, which is kind of
And we
cool,
sort of,
excellent. Is there another thing that you would like to mention regarding experiments or regarding the paper itself? Because we've been talking for a while.
So like if you go up, I mean a little bit up, just the figure that's just kind of hiding. I think this is also super neat. Figure, that one. So like Walid had the idea of kind of reducing the number of function iterations. Like instead of dropping functions, we just reduce the amount of compute at test time without any extra training. kind of like
The
dropping functions.
recurrent applications of
Right.
the functions.
Exactly.
That you
So
do.
we're kind of squeezing in height and not in width. Like previously we were squeezing in width by reducing the number of functions, but now we're squeezing in height and it works. And like I was super surprised to like it caught us by surprise, I think. Like so that was a fantastic lead. So yeah,
so this shows essentially as you can sort of you train with 8 recurrent iterations, but you can get away at inference time doing 7 or 6 or even 5, and performance essentially stays sort of the same. It's only when you go down to 1 or 2 that you really drag the performance down.
And think about it. Of course, it's not something you would want to do with this particular architecture. But the idea of this conditional compute and is really nice because it allows you to train your big library of functions, right? And now you have a task, and inference time is very important, right? So okay, I'm not going to do 8 iterations. I'm just going to do half, and of course it's going to be worse. But I don't need to retrain anything. Or I want to add capacity, I plug in this new module, or I have memory constraints, and then I cut half of them, right? This is fun, and I would like to see more of it in neural networks.
Did you try more than you trained with? Like doing 16 when you trained with 8?
Actually,
I think
Yeah, can you guys hear me? Yeah, we did do that, and we expected somewhat like that it might increase the accuracy. Not sure, I mean, that was unrealistic expectation, and it didn't do much, like it dropped a little. So we did go to 16. But
so it's fair to say like it works the best when it is as trained, but there is a variation you can do. Yeah, I see.
But at the same time, I think it'll be fun to figure out ways of like breaking that pattern. Like not having drop down, but at least like at least saturate. That would be nice.
Yeah.
Right.
It might be that if you train with only like 2 or 3, you might have maybe a bit of a chance, because it seems like just gauging from the plot, right? It seems at 8, even you train at 8, you already seem to be in kind of a regime where it's it has done its work.
Right.
I enjoyed reading this, and I very much enjoyed having you here. So
same here.
Thank you so much for being here, and I hope to see you again soon.
Thank you, Yannick.
Thanks, Yannick.
Thank you.
Yeah, it was amazing.